This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, let's start. This is week 5. Let's first revisit what we have learned so far. What we have learned? Nothing? What do we have learned? So we learned continuous time, discrete time. What we learned first? Signals. And then systems. And so first week we talk about basic understandings of signals and systems. We're talking about continuous time, discrete time systems, whether it's a periodic, finite duration signals, and also we talk about continuous part, discrete time part. And then we also talk about continuous time system, discrete time system. We also mentioned that, okay, what's linear time invariant system, whether it's with memory or without memory. So the first week is basic, very simple introduction of signals and system. So second week, we start to talk about systems. We talk about a very important concept, convolution. So convolution will tell you if I have, for continuous time system, impulse response, for discrete time system, unit pulse response, if I have those two signals, for the linear time invariant system, continuous, linear time invariant system, discrete time, I can always use convolution to compute. For given any input, I can compute output. That's the key idea of convolution. So why this is, if you look at chapter 1, Introduction of Signal System, chapter 2, Basic Convolution, chapter 3, Fourier Series Representation, chapter 4, Fourier Transform, and chapter 5, we are dealing with discrete time Fourier Transform. So 3, 4, 5, they are related to signals. Why? I want to consider my systems in the second chapter. Why? As I mentioned, the key idea of engineers is always trying to understand. I want to build a system. I want to check out for this input signal what my output signal would be. Or if I want this particular type of output signal, what this input signal should be. That's always what engineers can do. And if you consider most of cases, engineers are dealing with linear time invariant system. And they have to do convolution all the time. Yes?
Is there reverse convolution?
Sorry?
Is there the reverse of convolution?
So what do you mean reverse?
So you take a signal, you convolute it with the unit impulse response of the system, right, to get the output response?
Yeah.
And then is there a way, if we know the unit impulse response, to then do something with it, like an inverse convolution with the output response?
Well, okay. That's a really good idea because that's what we are dealing with system. So why we're talking about transforms, Fourier transform, you will learn Laplace transform as well. the key idea of these two transforms is they convert convolution to be multiplication in frequency domain or Laplace domain. So what it's trying to do is, here's my system. I got my impulse response, continuous time, unit pulse, discrete time. And this is signal. I will do transformations. And then here's my input signal. I can multiply them, calculate my output signal. I can do reverse way as well, because if I know my output transformation divided by my unit pulse response in discrete time or impulse response, I can calculate my input signal in frequency domain. I will do inverse Laplace or inverse Fourier transform. That's why this is very important. So in signal systems, and particularly when you are dealing with linear time invariant system, frequency domain is very, very important, because it will tell you information of the system. And also, as I mentioned, any signal engineers are measuring, they can't use directly, because every signal coming from particular system will have its frequency range. As I explained before, my frequency is representing the change of signal. So in this case, probably you already see some of my videos. We do rehabilitation robotic system. We're trying to hold stroke patient upper limb and try to, if the stroke patient is able to reach target, he will reach by himself. If he's not able to, my robotic system will generate a torque and support his arm to do the task. And then the first thing is you have to measure my position of my hand, my elbow, my shoulder. And you know it's a movement of my humans. So my velocity is limited. So my velocity is derivative of my position, somehow representing my frequency information. And you know how much or how fast a patient can move. And then you can, from this measurement, you can see, okay, my velocity of this patient is 10 kilometers per hour. That's impossible. Definitely it's noise. So you have to use this information to purify your signal, and you know that your signal measured from sensor has physical meanings. Those physical meanings are related to frequency. And that's why we really need frequency response, and Fourier transform is very, very important. And you probably see this kind of calculation maybe in advanced signal processing, advanced control system, all those things. You probably will see this in the subjects of electrical engineering. So that's why signal systems are probably a prerequisite for many subjects. All right, let's talk about what we are going to cover for this week. I think, as I mentioned, what I mentioned, these subjects have a very, really nice symmetric properties. So every time we talk about anything in continuous time, we will find the discrete time counterpart. So what we are doing is just repeating what we did last week, from continuous time signal to discrete time signal. That's why I think I was a little bit quick last week, because I was thinking about this week lecture. It's just the same thing, repeating. Okay. because you already know what is my Fourier transform for continuous time signal. So if, let me try to check out whether my document camera is working. So let's just start again from continuous time signal. So I have my continuous time signal, and I will have its Fourier transformations x omega. And I know my t is belong to R, and my omega is belong to R, and my x omega is a complex number. My xt is a real number. So, as we mentioned, under three conditions, the Fourier transform of this signal exists, and we can always write down my x omega is my integral from minus infinity to infinity, xt e minus j omega t. My integral variable is my dt. And if you consider a standard Fourier transform, not generalized Fourier transform, this signal will be a continuous time signal. My omega is always real number, this signal, because you take integral, this signal is continuous. If it's not continuous, we call a generalized Fourier transform. You see that my step signal does not satisfy one of the conditions. All the periodic signals do not satisfy one of the conditions for the existence of Fourier transform. That's why we introduce discontinuity functions in my Fourier transform, which we call generalized Fourier transform. Okay, so if you consider this case, we can easily consider here, we have signal in my discrete time, and I want to change everything into frequency domain as well. To make a difference between the continuous time domain and discrete time domain, we don't use a small omega, we use big omega. So if you do that, you will find out my frequency response of my omega will be exactly same as I will change anytime I see continuous time integral in discrete time, I will change it to summation. Thank you. So I will consider this part because my n, which is integers, will be my summation variable, and same, and I use small omega in continuous time. I will use big omega in my discrete time. I will have j here, same, and my variable instead of t will be n. So if you know how to get continuous time Fourier transform, it's very easy to extend to discrete time Fourier transform. Okay. So if you look at them, they are very similar. Here, x, e power, minus, and omega. So this is the third time we see similar things because, as I mentioned, first time, if you look at this, Fourier transform is an extension of my complex Fourier series representation. make sure that my capital T, which is my period, goes to infinity. You can get from Fourier series representation to my Fourier transform, and then it generates same things from continuous time signal to discrete time signal. So if you look at this one, question is, all right, why I can't write down as this one? So the interesting things for the discrete time Fourier transform is, even though my signal is in discrete time, my transformation is still in continuous time, because this part, only n, is integer, but my omega is a real value. So if you look at this kind of things, you can see n here is an integer, and omega is real value. So you have to remember, even though those two equations, they look very similar, this one is mapping from continuous time. T is belong to R. This one, n, is, I use capital Z to represent the set of integers. And this one is belong to R, and this one belong to R. Yes?
So what happens at the points where, say, n is an integer, what happens at the point 1.5? Because how does that map? Because you said x omega, big omega.
Yes, this big omega can be value, right?
Yes.
N is an integer, right?
Yes.
So omega can be 0.2, square root of 3, any real number. But only the variable. So my n is my summation variable. Yes, so this function is discrete time in n, continuous in omega. Okay, that's the difference. I want to highlight, they look very similar, and that's why we write down capital omega, and basically this signal is continuous time signal. Any question? So here is definition, and obviously if you look at this signal, so here is my discrete time Fourier transform, and this one n is independent of omega. And if I substitute so if I substitute omega by omega plus 2 pi, and if I'm saying is I substitute omega by omega plus 2 pi, this part will not change. And this part will be same, this part will not change. I only change this part, 1 omega, big omega to be omega plus 2 pi. And because my e power of minus g omega, anything, will be cosine plus j sine. And it's a periodic signal with period 2 pi. So that indicates my e minus g omega n will be so if you look at this case, I can always see that my Fourier transform of a discrete time signal is a periodic signal with periodicity with period 2 pi. Okay, let me slow down a bit. So you always have to know, okay, which is variable. If I change to the variable, which value I should consider. So let me just write it down again. I'm doing my discrete time signal Fourier transform. And when I substitute my omega, big omega by big omega plus 2 pi, I will have this summation same. Omega doesn't affect my n, keep this same value. And this part, I will substitute this big omega by big omega plus 2 pi, and this is n. And you know this function is periodic with period 2 pi, and that will be exactly is n equal to minus infinity xn e minus omega n. And this indicates my Fourier transform of discrete time signal is a periodic signal. That's simpler because I don't have to compute everything. I only need to compute from 0 to 2 pi or minus pi to pi, anything same length as 2 pi. Is that correct? Because it's periodic. So if you consider sampling, and if I sampled a periodic signal, possibly I can get a not periodic signal in discrete time. And after doing my discrete time Fourier transform, I got another periodic signal. Because my discrete time signal Fourier transform is always periodic. And that's why when you consider calculations, now you understand why engineers like to deal with discrete time signal. Because in frequency domain, it's much simpler. When you do Fourier transform for continuous time signal, you will have a very long frequency range. You calculate for every frequency. Every frequency you will have a different amplitude, different phase. However, when you convert signal from continuous one to discrete time one by doing sampling, digital sampling, I will simplify. I just need to calculate 2 pi time, 2 pi omega. Just my frequency is from 0 to 2 pi. I need to calculate this one, then other thing will repeat itself. All right. So the logic is any discrete time signal, if my discrete time signal Fourier transform exists, it will be a periodic one with period 2 pi. So if I'm doing inverse Fourier transform for the discrete time signal, I don't have to deal from minus infinity to infinity because my inverse Fourier transform. Okay, let me just try to look at document camera. So if we are looking at so this is my continuous signal. It's Fourier transform. Discrete time signal. It's Fourier transform. And let's look at what are inverse Fourier transform. Just hopefully by repeating you can remember. So once I have my x omega, I will change to my time signal. And my xt is 2 pi, my still integral minus infinity, infinity. And here is my x omega, e j omega t. Here, my integral variable will be d omega. So similarly, if I'm doing things from discrete time Fourier transform, my x big omega, I will get something discrete time signal. And similarly, I can always write down same. Do I have to change to summation? No, because my Fourier transform of my discrete time signal is continuous in omega. Okay, I will still use this part. I will have n here because this is my variable and d omega. However, this one is periodic. This one is also periodic with 2 pi. And that's why I can only need to compute everything from 0 to 2 pi. Or I can change this one to minus pi to pi. Is that? Sorry? Ah, yes, thank you very much. Yeah, it will be this big omega, this big omega, this big omega. This big omega, yes. Thank you very much. Yeah. Sorry? Yeah, the omega, yes. Everything here will be big omega. Yes, because it's in discrete time. All right. So that's what we see here. We will consider my inverse discrete time Fourier transform, not summation, but integral. Yes?
If x of n is in discrete time,
Yeah.
how does that become discrete?
Yeah, but this variable is discrete time. So when you are doing here, I'm doing integral over omega, and this is t will coming out here. And here, similarly, because this is a continuous function, and this is continuous in omega, and this n, only this n, is an integer, and then this one will convert to this value, and that's why we will use integral instead of summation. So that's why everything will look so similar, because my continuous time Fourier transform is continuous in omega, and my discrete time Fourier transform is also continuous in big omega. Okay. If you remember the logic, you can understand why sometimes you see summation, when sometimes you see integral. It's just because the signal you are playing with. When you're doing this one, the signal I'm playing with, my integral signal, is my omega. And this is continuous variable. And when I'm doing transformation, the variable I'm dealing with is my n. It's a discrete time variable, and that's why summation will appear. Okay. So this part I already showed that. And I'm not saying it's a fundamental period is 2 pi, but 2 pi definitely is one of the periods. It can be smaller than 2 pi for some signals. Okay. Any question? Let's look at same thing. Same thing as continuous time signal Fourier transform. Continuous time signal, we will have three conditions. First one is my signal take absolute value, integral from minus infinity to infinity will be smaller infinity. Second two condition is in any finite time interval, I have finite number of discontinuities. Third one is finite numbers maximum, minimum. And now you are dealing with discrete time signal. You don't have any issue with continuity because it's not already in discrete time. And then you have no issues with anything related to maximum and minimum. And that's why we only have one condition is instead of my integral, I will have my summation from minus infinity to infinity. This signal, discrete time signal, takes absolute value will be smaller than infinity. And if this condition is satisfied, we call this DFT is in the ordinary sense. Because similarly, you will have a generalized discrete time Fourier transform exist when signals do not satisfy this condition. And once this condition is satisfied, my frequency domain, big omega, my Fourier transform will be a continuous function with respect to this big omega. So any time limited signal, the signal has finite support, this summation will be always finite number. And that's why the discrete time Fourier transform exists in the ordinary sense. Questions? Questions? I didn't have time to go through some questions last time because I want to help you to prepare for the multiple choice questions. So let's go through, have some break to go through those questions. So I'm asking you questions about, here is my xt is not zero and only in finite time interval from 5 to 10. And I'm trying to generate this signal from finite duration to infinite duration. And I'm writing down here is my summation of t minus kd, and this signal, it's basically, I will shift this signal by d and keep shifting it by kd, and I will submit this one k from minus infinity to infinity, and my d is 3, and my statement is this yt is a periodic signal. True or false? Why? Just
Because D is 3, but the length of time interval is 5.
yes.
Therefore, you can't have it. It's more.
Yeah, so basically if I have xt and xt minus d, these two signals, they overlap. And if this is satisfied as a periodic signal, this d must larger than the duration of the signal. The duration of signal is 5. My d now is 3. But But if d is larger than 5, 5 or 10, so you have one signal, you shift another signal, you shift another signal. These two shifting signals, they are not overlap. And that's why you can see one signal, another signal, another signal. You can see the periodicity very clearly. And if here's signal, here's my shift signal, they overlapped together, and you keep overlapping it, and they are no longer periodic. Is that making sense? So this is a bit tricky question. Basically tells you, one, we do have very similar things in lecture notes, but in the lecture notes it says that my D is longer than the duration of this signal, so that when I put two signals after one signal and signal after shifted, they are not overlap, so that you can always keep the periodicity. Okay. Yes, question?
So even though they do overlap,
yeah.
Wouldn't that overlapping be consistently overlaps for the rest of the signal though?
No, not always. Okay, what I'm saying is if this is a periodic signal, what I'm concluding is for any signal. Right? Because if D is larger than 5, it's always a periodic signal, no matter what my xt could be. Whether continuous, discontinuous, doesn't matter. Right? However, when you are overlapped, there might be cases for particular xt that this signal after overlap is no longer a periodic signal, then that indicates this statement is wrong. So what I'm saying here, for true and false, that indicate if for the true case, every signal, everything is correct. For false case, is okay, I think it's wrong. I give you example to show that it's wrong. As you see in your problems manuals, basically say you have a counterexample. Counterexample to show false. So that is a simpler one. Let's do another one, a little bit, that is a little bit tricky one. Let's do another one, which is a little bit simpler. So the following discrete time system is time invariant. Is true or false? Easy, right? So if you see one of the coefficients of this y in this sequence will be something related to my variable n, if you consider this n, in continuous time it will be t, you have something t squared. And that indicates at different t, for continuous time version, it will be different solutions similar here for the different n. My discrete time solution, system solution, will depend on where my n would be. So this signal is this system is time varying system. Okay. So I had 5 multiple choice, true false questions. I think it's around average of these two, probably. I think first question is a little bit tricky. You have to understand those concepts. The second one is relatively straightforward. Okay. I will keep doing this one until you feel like, hopefully you will feel like more prepared. I couldn't see until, but you might give me a counterexample. All right. So here is a discrete time signal. And why we consider this signal, you have to know, we know 2 very important examples. One is exponentially decaying function in continuous time. We can find my Fourier transform easily. Another one is somehow exponentially decaying function in the discrete time, and we can find its Fourier transform easily. So here is the step, and I want to slow down, trying to give you more steps and hopefully can help you to understand. So my signal is this one. So you know this signal is a step signal, right? So first thing I would like to check is whether is satisfied, because as I highlight many times, look at the periodic signal. You don't have to check 3 conditions because lecture notes said so. But if it's not periodic signal, I'm doing transformation, I need to check conditions. So for the discrete time signal, first thing I want to check whether this condition is satisfied. So if you look at this part, it will be n from 0 to infinity a n. I can write down absolute value of n. And I only have this one satisfied if my a smaller than 1. What's this summation? 1 minus this part over 1. Yeah. All right. So this, if absolute value of a is smaller than 1, I can find my discrete time Fourier transform. And if my a is larger or equal to 1, no. So once this step is done, we can find my transformation. Let me find my transformation, and if I'm wrong, just trying to, I will consider summation n from minus infinity to infinity. I will have my xn, same e minus j, big omega, this n. And I will have, because my step signal it's only not 0 when my n is positive, so I'm considering here is from 0 to infinity, a n e minus j omega n. How to compute this one? All right. So if you look at a, e, I'm dealing with, okay, let me first write down here, is 0 to infinity. I will put n outside. I will have a, e minus j omega together, power of n. Am I correct? So sometimes when I'm writing things, what I'm thinking probably is not consistent to what I'm writing. So if I made a mistake, just let me know. So I put n outside. It will become a summation of power series, right? And I need to find out whether this absolute value is smaller than 1. So I'm considering it will be a, e, j omega. So this one, my real part is cosine omega. Imaginary part is minus sine omega. Real part square plus imaginary part square will be sine omega, big omega square, plus cosine omega square, square root. This value will be 1 because this one will have amplitude to be 1. So that indicates for a absolute value smaller than 1, the whole thing absolute value smaller than 1 as well. So I can use formula to calculate. it will be 1 minus A So it's a power series summation. And you have to check this amplitude is always equal to 1. That's why everything, if my A amplitude is smaller than 1, the summation exists. So one very interesting question. So if I'm doing this case without considering my step signal, is this correct? So if you consider everything with step, this part will going exponentially decaying. And if you consider my n goes to negative, that will be exponential increasing. That's why you only consider half signal this side, which makes sense. If you go the other side from minus infinity to infinity, it will be unbounded again. That's why this part is very important. Without this part, you can't find Fourier transform in ordinary sense. Is that correct? Okay. Any question? Any question? So you can see the slides are relatively simple, but there are many steps are not included in these slides. And you have to tell me in the exam that you can find summation to infinity or minus infinity exists. Okay. Now, once we have this part, what is my amplitude? What is my phase? What is my amplitude and what is my phase of this complex signal of omega? So I'm writing down here, it will be 1A cosine omega plus A sine omega. So I will use Euler formula to write G e power of minus j omega into cosine big omega sine big omega. Then my amplitude, this is my real part, this is my imaginary part, right? So if you look at signal, this part without j, it will be real. So 1 minus a cosine omega is my real part. This part is my imaginary part. And when I'm calculate the amplitude, what this value should be, so my x omega will be square root of real part square plus imaginary part square. So 1 minus cosine omega that's a correct answer. If you give me this answer, I'll give you full mark. Of course, you can keep simplifying this one because I have 1 here. I have a square cosine omega square, and I have a square sine omega square. They both positive. It will be another 1. And then I have this crossover term, 2 cosine, a cosine omega. And what is my phase? So my complex number,
1 plus a squared.
yes, sorry, It's a squared, yes, correct. So if you consider the phase, so my complex number appears in my denominator. So I will calculate this complex number phase and put minus sign here. So I will have minus tangent inverse. My imaginary part is my a sine omega. My real part is 1 minus a cosine omega. If my real part is positive. And if my real part is negative, I will add 2 pi. So we'll have minus pi minus tangent inverse, same thing. So I have repeated many times how to compute the amplitude and the phase. I think I post on LMS 4 complex numbers at each corner of, and you can figure out what my phase, and from that example you might be able to remember how to compute the amplitude and phase. All right. So for the different omega, you get this figure. My amplitude and my phase, you get my spectrum. That's why here is the graph. So you can see here, and this value, my x omega, and because this is always bounded, and this value is always smaller than, for different a, you can think about this is something is a minus 1 square, and this part is between minus 1 to 1. So it's some, you can draw this spectrum out to have this x omega, and it's always for this value, different omega, you can have different amplitude, and similarly, for the different omega, you will have different phase, and you can have my angle, or we can consider the phase spectrum. This is my amplitude spectrum. Yes? Yeah. Yeah.
How come you didn't have to flip it to nominate, flip the bottom right to the top by multiplying by the conjugate?
You can do similar things. This one is easier. So what I'm saying is, if I have my numerator is constant, not necessary to be 1, you can always consider calculate my phase of my denominator, and then add minus sign. No, because I can always consider this function multiply its inverse will be 1. So then the 1 is corresponding to my phase is 0. So if you consider 2 complex numbers multiplied together, they will be basically magnitude multiplied together and phase shift. So basically this 2 phase shift adding together will be 0. So 1 will be minus other one. That's why this one is always easier. If you see, my complex numbers will have denominator complex, numerator constant. I only need to calculate my phase of my denominator and add minus sign. That's most straightforward to calculate. Of course, you can always convert to real part, imaginary part, use the same thing again, but this one is most straightforward or simple way to do. All right, I will stop here for today. And I see you tomorrow. Do you need extra tutorial before the semester, or because I didn't see many